geometric representation looks very similar. We have a complex number that has the real part A and the imaginary part equal to VI. And notice we can represent that by considering the distance from the origin to that complex number and call it R. And of course, that's very similar to the modulus. In fact, it is the modulus, but it's just simply represented by R. That means that distance from there to there, and by the angle relative to the positive real axis. Now when we do that, we can say that A now be calculated to be R times the cosine of theta, and B can be calculated to be R times the sine of theta. And since C, the complex number is equal to A, we can replace A by this and B by this, and then get the new polar representation of the complex number. Let's do that and see what it looks like. C now becomes equal to A, which is R times the cosine of theta plus VI, and B is R times the sine of theta, but now it looks better if we put the I in front. So we're going to put the I in front, so I times R times the sine of theta. Notice that each of these two terms has an R in it. We can factor it out. So C becomes equal to R times the cosine of theta plus I times the sine of theta. So this becomes the polar representation of that complex number. Now let's investigate the value of R and theta. Now R can be said to be equal to the modulus, which is equal to the square root of A squared plus B squared. So it's basically using Pythagorean theorem to get the value of R. And we can represent the angle theta by saying that tangent of theta is equal to the opposite over the adjacent. The opposite is B, the adjacent is A, so this can be written as B over A. Or we can solve that for theta and say that theta is equal to the inverse tangent of B over A. Now, theta can also be defined as the argument of that complex number. So that's probably a name or expression we should become familiar with. So that's the polar representation of a complex number. We can take the number Z equals A plus VI, and that is Z equals R, the distance from the origin, to the complex number in graphical format, times the cosine of theta plus I times the sine of theta. And again, they rather put the I in front, so you don't get confused with calling the angle a complex, the complex part of the angle. You want to therefore put the I in the front, so there's no confusion. And that's how it's done. Welcome to our lecture online. So you may wonder, why do we need virtual work? Can we use it for something? Is it useful? Yes, it is. In the case of particles or systems at equilibrium, virtual work can be used to determine the forces on the particle or on the system. So let's take a simple example. Let's say we have a beam, and let's assume that the mass of the beam can be ignored relative to the force acting on the beam. The length of the beam is L, and it's supported at A and at B, so we're going to have two reactionary forces, one at A and one at B. And there's a force applied on the beam, straight down, and this moves A away from the left edge of the beam, and the question is, what is the reactionary force at B? Now, of course, we have learned all kinds of methods to find that rather easily. But of course, we're going to show you how to do it using virtual work on this very simple example, so that later on we can do it on much more complicated examples. And you'll see that some of those complicated examples, using the virtual work concept is actually easier than using some of these other concepts that we have learned before earlier in the course. So, how do we do it using virtual work? Well, we start with the definition that if particles or systems are at equilibrium, that means there is no net force acting on it. That means that the virtual work done is going to be equal to zero. And we can define it as being equal to the sum of all the forces acting on the system. And so that would be the forces, let's call it some I, from I equals 1 to n, and we're going to dot those forces with du. So we're going to have a dot product between each of the forces acting on the system, and then multiplying it times the small imaginary displacement du. And we know that's going to be equal to zero. So let's go ahead and do that. Now there are three forces, one here, one there, and one there. And so when we have a dot product, we multiply the magnitude of the force times the displacement times the cosine of the angle between them. So starting with the first force, the reactionary force at A, and let me show you what we're doing here is we're moving the beam an imaginary distance just on the one side where the reactionary force at B is. We're not moving it over here at A, so this force here will not be doing any virtual work because that part of the beam will not actually be moving, or even it won't be moving in an imaginary sense, so stay stationary. So let's add up all the three dot products. So the first one will be the magnitude of the reactionary force at A times the displacement, so we multiply the times the displacement will be zero, and so we don't have to do anything else there. Then next we're going to take the force here, so that would be plus the magnitude of the force pushing down, times the displacement. Now how much did this displace? Well, if at the end of the beam here the displacement is du, we have to take a fraction of that, and the fraction will be A divided by L. So the magnitude of the displacement will be the fraction A over L times du, times the cosine of the angle between the two. Now the force is acting downward, and D is acting upward. The angle is 180 degrees, which means we're going to multiply this times the cosine of 180 degrees. Then plus, see here, now we have the reactionary force of D, so we have the magnitude of R sub D, times the displacement, again, that's imaginary displacement, and in this case, it is indeed du, so all du, times the cosine of the angle between the two, and And notice they're both pointing in the same direction. The angle is 0, so it'll be the cosine of 0 degrees. Now this part is 0, and of course all that adds up to 0, because the vertical work done on a particle or a system that is at equilibrium, the vertical work done will always be equal to 0. So this term is 0, and here the cosine of 180 is minus 1, so this becomes minus f times a over L. Oh, and let's see here. What else do we do? Well, we have a du in each term, so since that's pretty equal to 0, the du's cancel, so it doesn't really matter how much we move or make the vertical movement, we can cancel out the du, so we have f times a over L times the cosine of 180, which is minus 1, that's where this minus came from, and then here we have plus r sub b, the reaction force of b, times the cosine of 0, which is 1, and then that's up to 0. And all we have to do is move this term to the other side, so therefore the magnitude of the reaction force of b is equal to a over L times the force applied to the b. Notice, it's actually quite nice. It works very slick. And notice that even on this simple example, you can see the beauty of the technique. Actually, well, I have much better ways to do that, which is fine. We can use moments or torques or anything like that. But this works for even much more complicated examples. So we'll work our way to the more complicated ones to show you how nice the technique this actually can be. But now you can see how it actually works in a very simple example. And that's how it's done. Welcome to Lecture Online. As we hinted in the previous video, there are situations where we can use virtual work when the particle or the thrust that we're considering is at equilibrium and when the system is not at equilibrium. So in other words, there are two situations where the concept of virtual work can be applied. It's probably most useful when you have a situation where things are at equilibrium. So the first case, we're going to consider when the particle is at equilibrium, which means that the net force acting on the particle must be equal to 0, and if there's no net force, then there's no acceleration, so the m times a term in the second law must also equal 0. Which means that if you add all the forces acting on a particle or acting on a particular point in the flux, we can assume, or in the system, whatever system we're looking at, we can assume that if you add all forces, it is that of 0, and therefore we can say that the virtual work done, the delta value, is equal to the sum of all the forces multiplied by a small imaginary distance that we're going to allow the particle or the system to move through. So in other words, if we do a dot product between the imaginary displacement and each of the forces acting on the particle, when we sum them all up, that should equal 0, which means that the virtual work is equal to 0 when the particle is at equilibrium. But we can have situations where the particle is not at equilibrium. So the net force is not equal to 0, and therefore there will be an acceleration. F net is equal to the mass of the particle times the acceleration. But now we can also say that the virtual work can also be equal to 0 if we look at it this way. The virtual work can now be defined as being equal to delta W, which is equal to the sum of all the forces acting on the particle times the small imaginary virtual distance of displacement, delta U, minus this term, m times a, times the small imaginary displacement as well. Now that makes sense because if the total net force is equal to m times a, and this of course represents the net force, then of course, if I move the ma to the left side of the equation, I end up with f net minus ma is equal to 0. In other words, what's inside the parentheses here must be equal to 0 because this is the net force minus the mass times the acceleration of the particle. And then if we take that and multiply that via the dot product times the small imaginary displacement, this then represents virtual work, and this is then also equal 0 because this term will equal 0. In other words, it acts like it's a net force equal to 0. When we subtract from that, that's ma term. Now, what do we call that ma term? That ma term is called the inertial force. So we turn it into a force, we subtract it from the sum of all the other forces acting on the particle, and then the virtual work again can be defined as this times dot delta U, which also will equal 0. So in both cases, the virtual work will equal 0, but when the particle is not at equilibrium, we have to take into account this what we call inertial force portion. And that's how it's done. Welcome to our lecture line. Now let's take a look at a few more rules with conjugates. The third rule tells us that when we take a complex number and raise it to an exponent, and then take the conjugate of that, that should equal the conjugate of that complex number raised to the same exponent. And this rule we're already familiar with, that if we take a complex number and multiply it times its conjugate, we should get the modulo squared. So we'll illustrate that with a few examples. Here we're going to take z equals 3 minus 4i. We're going to let n equals 2. So again, we can do that with any number n, but let n equals 2, which is a little bit easier. And so we take we multiply z by itself. That means z to the second power is going to be equal to 3 minus 4i multiplied times 3 minus 4i. And if we then take this product and take the conjugate of that, that should equal the conjugate of z squared. Let's see if that is the case. So first we're going to multiply these together. This is 3 times 3, which is 9. minus 16, which is minus 7 minus 24i. And if we now take the conjugate of that, so we take the conjugate of this, which is a conjugate of that, conjugate of this, and this, and this gives us minus 7 plus 24i. So now what we're going to do is we're going to take the conjugate of z and square it and see if we get the very same result. Alright, so the conjugate of z is equal to 3 plus 4i. So the conjugate of z squared is equal to 3 plus 4i, multiply times 3 plus 4i. This is equal to 9 plus 12i plus 12i plus 16i squared. So this is equal to 9 plus 24i, and this is I squared is negative 1, so negative 1 times 16 is minus 16. So this is minus 7 plus 24i, and notice that, yes indeed, minus 7 plus 24i, minus 7 plus 24i, they're equal to one another. So this has been illustrated with a simple example, not proved, but at least illustrated. So now let's go ahead and look at this rule. We're going to take the z and multiply times its conjugate and see what we get. So z times its conjugate is going to be equal to 3 minus 4i times 3 plus 4i. And of course, we then realize that the middle term will disappear. This is equal to 9 plus 12i minus 12i minus 16i squared. These two will cancel each other out. This becomes 9 plus 16, since I squared is negative 1, and negative 1 times negative 16 gives us a plus 16, so this becomes equal to 25. Now, do we get the same result when we take the modulus and square it? Well, the modulus of z is defined as the square root of a squared plus b squared, the magnitude of the real part squared plus the magnitude of the imaginary part squared. So let's see that. This is equal to the square root of 3 squared plus the magnitude of, that would be minus 4 squared, which is equal to the square root of 9 plus 16, which is the square root of 25. Now, if we take that result and square it, then see that modulus squared is equal to the square root of 25 squared, which is equal to 25. And that gives us the same result as we had before. Again, you can see that that works out as well. A simple example. That's how it's done. 0. And so we have f1 du, which is a positive quantity because it multiplies out the cosine of 0, minus f2 du because this is a negative quantity, the cosine of 180 is negative 1. Then, since we have the two members f1 and f2 of equal magnitude, then when we add these two up together, we get left d0, which means that the virtual work done on this object has moved a small distance of the u is actually equal to 0. And as we'll see later, that is one of the benefits of using the virtual work concept, because when objects are at equilibrium, when a particle is at equilibrium, when a truss is at equilibrium, we can then say that the virtual work done by moving the members of a truss, for example, a small amount of distance, the total work done will then be equal to 0, and that then will enable us to find the forces on those members. So there's actually a useful technique here that we can apply to find forces on more complicated structures. So the concept of virtual work is that a bunch of forces act at a particle or act at a particular point of a truss or something like that. If we then imagine that we then move that point, move that particle a small amount of distance, an imaginary distance that we don't move it, how much work would those forces then do? When we add them all up, and the particle or the truss is at equilibrium, not moving, not accelerating, then the sum of all those will add up to 0. That's what we mean by virtual work done. In this case, on a particle at equilibrium, but it can be done on a particle that's not at equilibrium. And we'll see later how to do that as well. That's how it's done. in imaginary plane the values of 2 plus 3i and 3 minus I on both these graphs. Now, if we represent these by vectors, because adding complex numbers is very similar to adding vectors. So we're going to draw a line to this point right here from the origin. This line is going to represent the complex number 2 plus 3i. This vector has an x component or a real component of 2 units and an imaginary component of 3 units. Likewise here, we can draw a vector, and notice that we have a real component of 3 units and an imaginary component of 1 unit in the negative direction. So when we add these together, it's almost like adding vectors together. We can take this vector and slide it over there, and this, and notice that if we add these together, the sum should equal this right here, which is basically 5 units in the x direction and 2 units in the imaginary, or the real direction and 2 units